Welcome to Theory of Computation class. Here I am giving the explanation for the theorem under LD, diagonal language. So if you consider LD is a diagonal language which contains a set of strings. The set of strings are framed with the complement of the diagonal values of square matrix, and no strings are accepted by any of the machine. So those type of strings are framed as LD. And the theorem says that LD is not recursively enumerable and not recursive. So I want to solve this theorem. So I am going to take the proof as a contradiction method. Contradiction means true means false, false means true. It is a contradiction. So I am going to take a contradiction method. In case 1, I try to prove LD is not recursively enumerable. So I considered as LD is recursively enumerable. So if you consider LD is recursively enumerable, the machine M and the language is LD, I am going to give a string as W. If the machine accept this language means it will go to S state. If the machine not accept that language means it will go to looping state. It is the recursively enumerable generalized form. But if you take the definition of a diagonal language, consider the definition of diagonal language which contains a set of strings and no strings are accepted by the machine. So if you give set of strings which are all framed under diagonal language, that machine, any machine that will not accept that set of strings. So there is a contradiction for this recursively enumerable notation. So LD is only a not recursively enumerable language. And consider case 2. I am also going to take a contradiction formula. So consider LD is recursive. So if a language is recursive, the machine goes to S state or no state, depending upon the answer. But from the same definition, that particular set of strings will not accepted by the machine. So there is no possibility of S statement for the given string. So here also there is a contradiction. So LD is not recursive. So by using case 1 and case 2, we proved the theorem as LD is only a not recursive enumerable language and it is not recursive. Consider another type of language. It is universal language, LU. It is also called as a reprogrammable language. So what is the meaning of reprogrammable? Means it is a simulation of other languages. So what are the other languages? Here I only know about a diagonal language. Then other languages are empty language, non-empty language or complement of diagonal language. So these are all different type of languages. So if you consider universal language, it is only a reprogrammable language. That means that it will work with the simulation of these 4 types of languages. Either these languages or it may be recursive language like that. So LU is a universal language which accepts W, but the W can be accepted either at LD or LD bar or LE or LNE. So it is only acting as a simulation of other languages. So that only it is called as reprogrammable language. So what are the conditions for framing a universal Turing machine? Means that a universal Turing machine should be in an encoded format. Encoded format means the set of states and set of input symbols and also the directions. So all these values should be in an encoding format. So the generalized encoding format M is equal to 111 and each notation's encoding format, and finally it should be end with 111. So this is the encoding format. So we can only implement the Turing machine in an encoding format, and if you want to solve a universal Turing machine, then that machine should contain a multi-tape format. That means instead of a single tape, we can use 3 tapes. One tape is used for storing input symbol, and another one is for set of states, and another one is for replacement symbols. So using these 3 different tapes or 4 different tapes, multiple tapes, we can able to solve the universal language notations. So all values should be written in a binary string format. So here there is a theorem which is related to universal language, LU. So LU is recursively enumerable but not recursive. So how can we prove it? So we already know that universal language should be solved with 2 different conditions. One condition is it should write in a multi-tape Turing machine, and we should write it in an encoding format. So LU is solved with a multi-tape Turing machine. So 3 tapes are necessary. Tape 1 contains a set of input strings. That input strings are in binary format with readable mode. Tape 2 contains set of states Q in each notation, but that tape contains a rewritable mode. So you can able to replace one state with another state. Tape 3 contains replacement symbols, which is also under a rewritable mode. So if you consider 3 different tapes, only tape 1 contains a read mode, tape 2 and tape 3 are rewritable mode. And if you want to write an encoding format, the generalized format is IJKLM. So that will be written as tilde of QI, AJ, QK, XL, DM, where I, K are states, J, L are tape symbols, and M is the direction. So we already know the encoding format notation. And also by the definition, LU is not a new language, it is a reprogrammable language. So it will act like either empty, non-empty, diagonal, or the complement of diagonal language. So the answers of any one of these languages same for LU. So LU is only recursively enumerable. And another condition is the universal language is a simulation language. So the output of LU is depending upon that simulated language. So that simulated languages may be either these 4. So we cannot able to predict the exact output based upon the functionality of any one of these 4 languages. LU will give the output. So therefore LU is not recursive. So hence we can solve the proof for LU because LU is only recursively enumerable and not recursive. Thank you.